Okay, welcome back. Unless there's any questions about yesterday's material, I would then get started with the next chapter, which is a general theory for invariant manifolds in higher dimensions. Any question? Again, this was my scribbles from yesterday. A bit hastily made, but hopefully you got the point. The writing is somewhat better in the notes as usual. But I mean, we ended on this note, and even before I leave this, I mean, just to motivate the next subject, there's invariant manifolds in this picture everywhere. And in very little of the material that I've been covering for a while is about individual trajectories. It's everything I'm drawing here. A torus is an invariant manifold, right? I'm using these trajectories to illustrate that it's filled with quasi-periodic trajectories, but that's not the main point. You know, the individual barriers don't have the capacity to individual trajectories to serve as barriers, say, to diffusion or transport in the phase space. So that's an invariant manifold. All these are invariant manifolds, right? Everything involved in this picture is an invariant manifold. When you actually look at the numerics, you see little dots of trajectories. Unless they form some sort of coherent invariant surface, they don't seem to be that significant. You don't really realize their role. You start realizing roles of dynamical objects when actually they form invariant manifolds, like these curves, right? So if you really think about it, same here, the gap, right, is invariant manifold or leg thereof. Already, you see that in all these contexts, what really matters is not the individual evolution of those trajectories. I mean, those are sensitive to initial conditions anyway, but rather the structure of the phase space is determined by invariant manifolds in general. So motivated by that thought, I'd like to move, what's the title? Move on to, again, any questions?
If I may, yes. Am I audible? Yeah?
Yeah.
Thank you very much. So just loosely connected to the Hamiltonians, yesterday evening I checked into the lecture of Russ Tedrick at MIT, who's doing electrobotics there, and he mentioned piecewise Hamiltonian systems that are moving between different manifolds. Mm-hmm. I guess he was talking about a robot which introduces forces only at times and then stays at one manifold, relaxes, and then jumps to another. And I just found that a weird concept in stability analysis. I feel that it's a kind of it violates the whole Hamiltonian point of having a nice conservative system and leaving it there. Can one just examine the different steps of these systems and arrive at stability conclusions and build that work? Because he kind of implied that, and I
not that I know of. I mean, the classic example is, I mean, I don't know his context. He probably knows what he's doing. I don't know him. But it's very hard to pass judgment. I don't see that. But the classic example, was the impact oscillator. If you think about it, that if this little problem in which I think we were talking about recurrence. This is a Hamiltonian system so far, right? It's just a linear oscillator, a conservative linear oscillator. And it would oscillate as a Hamiltonian system. And if you then insert a wall here and it starts making impacts, then it will still be a piecewise Hamiltonian system between impacts, right? Now, if remember what the phase portrait for this oscillator would be, if the unstretched equilibrium is somewhere here, then these are the level curves in the phase portrait. These can obviously be nonlinear as well, and it's supposed to be symmetric. And the way to understand this system would be is that you simply block this part of the phase portrait, right? And then you can still view this as a piecewise Hamiltonian system between impacts. So you evolve here you evolve here and then you hit the wall, right? We were talking about the case when, and this is now starting to become relevant to stability, when the impact here was perfect. When the impact here was perfect, then, sorry about my picture, this is clearly positions and these are velocities, and I should have perfect symmetry, which I don't have. But if you have a perfect impact, when you come in with some velocity, you jump on the other side, it's going to be the exact same velocity. So despite my picture, you should be moving on the same periodic orbit, and energy will be conserved. And you can view this as a unit of Hamiltonian systems on the same energy level, right? When the impact is not perfect, then you're not on the same energy level after the impact. So you come in here, okay, with some velocity, and your velocity will decrease. So you jump to the negative part, and I should exaggerate this a little bit because so you jump here, right? So the point being that this velocity, your incoming velocity, was larger than your outgoing velocity. So that would then put you on a lower energy orbit. Okay, so you would be going here. So now you're Hamiltonian, right? But next time you hit this, you're hitting it there. Again, you're losing energy. So you see what I'm doing, right? So you're spiraling inwards and you're losing energy. And in particular, if that wall happens to be right here, so maybe I try to do a better job now so if the impact location is right at the unstretched equilibrium point, okay, then what will happen is you come in on a Hamiltonian orbit like that, you jump in the other direction. So here's the sort of the I mean to convey is that here's the zero velocity line. So this would be v equals 0, right? So you come in and you jump, and when you jump in the velocity, you're losing energy. So because it's a non-perfect impact, so your orbit will be something like this. You jump on the other side, maybe here, and then again you do your Hamiltonian flight, and then you again jump here. And you hopefully see the point that in this case, this equilibrium point here becomes asymptotically stable, even though it was only the Lyapunov stable before that. Okay. So you can't change the stability type if you're only piecewise Hamiltonian. Okay, it's all about the switch. Does that switch from one Hamiltonian system to the other, does that switch preserve the energy? If it does, then you do the proper framework. That can be a legitimate way to compute the stability. Even then, it's not something trivial, but it could be. But in this way, you would essentially spiral into that equilibrium point. So you're changing the stability type of that. Okay. Anything else?
Just another thing about this this lecture that I just had. Most of the time, they seem to stick to linear stability analysis in Hamiltonian systems, and in the homework we've seen that it's very, very easy to find Lyapunov functions and to do it in a nonlinear way. Is there any motivation for engineers to stick to linear stability analysis other than being...
So if it's the Hamiltonian system, you're talking about the Hamiltonian context. If it's the Hamiltonian system and you know that the energy has a minimum there, then there's no need for nonlinear stability analysis. That's what we have learned. Because automatically you have a Lyapunov function, which is the Hamiltonian, and it will qualify and prove stability. So all you need for the energy to have for the Hamiltonian, that is, to have a maximum or minimum.
Yeah, that was my point. Sorry, I did not phrase that correctly. So they did not really approach stability from this context. They still tried to do the linearization and then the eigenvalues.
Because maybe in the class of problems that they are looking at, it's a given that it's always, I don't know, again. Generally speaking, that's not correct. Generally speaking, if you have Hamiltonians that don't have an extremum there, then nonlinear stability is an issue. Okay, so if you have gyroscopes in the system and the like, then it's by no means given. And if you have the appropriate dimension, you're over 2 degrees of freedom, you're 3 or higher, generically you're not stable. It means that there will be always these trajectories that I have shown here that sneak out. That's just a fact. You can't do anything about it. So that topological instability is generic from 3 degrees of freedom or higher if the Hamiltonian is not definite at the equilibrium point. Okay, so that is a fact. And also, one then also should worry about the model itself. It's the Hamiltonian is not definite that the slightest dissipation, right, will destabilize the system, again, generically, for the reasons that I have shown you, that it's no longer an energy sphere that you have around the origin, but these open energy surfaces, right? So for all these reasons, in fact, the conclusion, stability conclusion is not really defendable physically unless the Hamiltonian is definite, okay? Because slightest imperfection in your modeling will take you away. And again, the tippy top is sort of the paradigm example.
Okay, thank you very
much. To be honest, though, I mean, the people in the nonlinear controls should know that or would know that, but I do know mechanics books in which, pretty well-cited mechanics books in which people analyze the stability of a gyroscope or the shaft over critical speed, and they do a linear stability analysis. They get these purely matching eigenvalues and they proclaim the system to be stable, and that's incorrect. You don't know that. In fact, in those problems, you really don't know because the Hamiltonian is indefinite. Okay. Anything else? So thanks for the questions. So again, hopefully you just really think about what we've been doing so far in this class. It's really already one way or another about invariant manifolds. So let's see what we can say about them in general. And you've already, from the last chapter, you've already seen that not all invariant manifolds are nice in the sense that they automatically persist on the perturbations. Just look at this very example here. All I did, I had infinitely many of these guys before I added the nonlinearities, and I'm still close to the origin, right? And yet they got decimated. They got completely decimated. So it's not true that just because I have an invariant manifold that, oh boy, I'm done because it's enough to look at invariant manifolds, they are robust. No, that's by no means the case. So that's why we need, in fact, a chapter to see what are the invariant manifolds that are in fact robust, and then take over this role of robust organizing centers in our understanding of dynamics. So even under perturbations, they would be there. And there's a class of these manifolds, and they're called normally hyperbolic invariant manifolds. I think this is too thick at this point to get it down. So this is I think this third chapter or so. This is normally hyperbolic invariant manifolds. And this is a long term, so people just started calling them NHIMs. If you can read that, you can. I can't. So that's an acronym for normally hyperbolic invariant manifolds. Okay, so the objective would be to extend what we've seen in lower dimensional example. And specifically, well, what I won't be able to do is extend in this theory the notion of an elliptic type invariant manifold, the Km tori, in a more general sense than what we already have. That's pretty general already, right? But I can't just extend that to invariant spheres and other compact sets that have a neutral stability type. That unfortunately doesn't work. But I can extend the notion of stable and unstable manifolds to higher dimensionals, so that they are stable and unstable manifolds of not fixed points, but pretty much of anything. So stable and unstable manifolds. To a general higher dimensional setting. There's no need to extend the notion of a stable mouse to a manifold of fixed points. We have seen that in, you know, in any dimension. In only dynamics 1, I had a theorem, the center manifold theorem, that tells you that they exist under what conditions. But fixed points are very small, low-dimensional objects. Can I have stable unstables of manifolds, or can I just have invariant manifolds that are robustly there? And why do we care about manifolds? So this is, again, just a small example about the significance of invariant manifolds in general. I mean, generally speaking, they are more observable and more influential and more robust. And then I have to say, then what, right? Then trajectories. And you know, a really simple example would be, and you know, connected all these statements to reality, and not just say, well, I'd like to work with the invariant manifolds because they're more robust, and I'm a purist, I like robust things. No, that's actually a very practical thing, that if you have, say, reality, which this is your real dynamics, all right? So let's just call it reality. Let's call it true dynamics instead, which you would like to model. You always just model the true dynamics. You never know exactly, right? You're always making small approximations and things like that. So then you say, all right, so then I come up with something and I do my best and I come up with a model. And that the model dynamics, let's just assume it's pretty close. Put it on the other side to be consistent, I think, with the nodes, but not that it makes a difference. So just imagine if you actually had a nonlinear model that mimics a system, a true system like this, then you would really be doing very well, right? So this would be the model dynamics. And if this was the case, then I would call this a very good model. So this is a good model. It means a differential equation that by and large really gets the saddle type nature of this thing. But even then, now imagine that you pick an initial condition somewhere here, and you have a very good model, and you happen to pick this initial condition. So this is a common initial condition. And you do what, in fact, most people in a lot of areas would do. They would say, all right, I have a model and I know an initial condition and I have an observation for that. Say I've seen a float in the ocean, or I've seen a particular outcome in the mechanical system for that particular initial condition. Is my model good enough? Is it reproducing that outcome, right? So what I observed in the real model, of course, from that initial condition was this type of a dynamics, right? So the evolution, this is the true evolution, right, of the initial condition. Now let me test my model. And then you say, okay, so I launch a model trajectory from the same one and I follow my model. So what will the model do? This. So this would be the model evolution. The same initial condition. Now look at it. So one went this way, the other one did the complete opposite, so to speak. And you could say, all right, so this is a bad model. Is it really a bad model? No, it's a very good model, but you were looking at the wrong thing, because trajectories by themselves in a generic dynamical system have sensitive dependence on initial condition, no matter what you do, right? Even if you worked in the same true reality and you had the perfect differential equations, you make the slightest change in the initial position, or in an unsteady system, in a non-autonomous system, the slightest change in the initial time, you would end up at a completely different location after a while. So this is not the right way to test the robustness of a model. why did we presumably all agree at the beginning that this was a good model? Because I purposefully didn't show individual outcomes, but I showed the invariant manifolds that define the phase space structure both in reality and in the model, and they were very close to each other. So what really matters is, for the particular analysis that I want to be doing here, overall prediction, is that look at this unstable manifold here, okay, like that, and then look at this other unstable manifold here, which are very close to each other, right? So as a result of that, so let me just point that out, but the two unstable manifolds are very close. So why should I be happy with that when I didn't get my individual evolution right? Because let's not get focused so much on individual evolutions. You didn't know, chances are you did, very good chance that you never knew that initial position exactly anyway. You had measurements errors and whatnot, and you were never interested in exactly where that particular thing goes, but overall what the system behavior is. And when that's your interest, as it normally should be, then look what happens, that in the model, there will be a spray of trajectories that you release, and they will be all blocked by this curve. And in reality, the same thing will happen. Say, even release it from the other side. You're probing what the behavior of the system is. You will see this, we could call this a front, right? And they're incredibly close to each other. So the behaviors, the ultimate asymptotic behaviors, even over short times, that the nature of the behavior is very well modeled by the system, right? And that's why we care about invariant manifolds. So I would say that are very close. So typical behaviors are close qualitatively. Because even in your model, right, if you change your initial, even in your reality, you went this way with the real trajectory, and you also went this way with the other one. But if you then change slightly initial conditions on the other side, you would go this way. So it's not so much left or right, but what are you accumulating on, say, a front? And that would be an observation in the ocean, for instance, or in the atmosphere. Okay, so that's why we care about them, and that's why, and in this case, you see that the invariant manifold robustly survived in the model, even though individual trajectories had no robustness whatsoever. Okay, and we can't expect that anyway because we have sensitive dependence on initial conditions. So in general, so these the star features cannot be expected for individual trajectories. Okay, so then this brings up the question that what are the types of invariant manifolds that are like this, and the term for these is persistent. So they really persist even if you really just have a model or you have some uncertainty on the model. So what types of invariant manifolds are persistent? And as it turns out, this is the class, this is the title of the class that I have already given out, the normally hyperbolic invariant manifolds, the NHIMs that have that property. But before I answer that, it's a bit technical to say what a normally hyperbolic invariant manifold is and to state their theorem. I'm not going to do any proofs, but at least state them. I need to even just say first what's a manifold, right? I've been talking about that, but to get a bit more technical, I want to do a little bit of a crash course in differential geometry. Which, for those of you who haven't seen differential geometry, might be useful in its own right. So it's a crash course, so it's going to be very short. but hopefully you will get the main idea about the structures that we're using. Well, the very first thing is, what's a manifold? Okay, so let me just say what the definition is first, and then I'll explain. There is an abstract theory of manifolds which allows the definition of a manifold in an arbitrary space. That gets very abstract very quickly, and it's beautiful mathematically, but excuse me, we have no use of that in our setting here. So I would go with the easier version, which says that whatever that object is, it's placed in a Euclidean space, okay, to begin with. So the ambient space that we have in which this thing lives, that I don't know yet what it is, it's nice. I can do multivariable calculus on that, right? But just so that you know, there's a way to define manifolds that doesn't assume that there's a nice ambient space. So it's just really that thing directly. So this lives in Rn, I should say, not Rk, this set M, and we will call is a k-dimensional, and k is another integer here, and that will be manifold. In the notes I said, and in parentheses, I said, sometimes people say differentiable manifold, because there are also definitions of manifolds that allow for non-differentiability. But again, here in this setting, we need differentiability. But when people say manifold, it's usually mean differentiable. So that's the definition here. And first, the easy way of saying it, if, and this is I think the definition you should remember, the first approximation, if it is locally diffeomorphic to that Rk, k was this integer here. You see the role of that now. So diffeomorphic means that it locally looks like that, so up to smooth deformations, right? So to work that out a little bit, so what does this mean? So this is the IE here. IE, for any point in this set that I'm now planning to call a manifold, there exists an open neighborhood of X in M, and this will require some explanation. What is it to be open with respect to a set which is not the ambient space that I know well, but potentially a pretty bad set? Well, I'll come back to that. But it's an open neighborhood of X in M, and I need to give a name to that. So this, let me move this a little bit. That's the V neighborhood, such that V is diffeomorphic, which means there exists a diffeomorphism taking it to an open set U in Rk. So I can locally model the manifold locally always as an open set of Rk up to smooth deformation. So I live in this general ambient space that I have picked at the beginning. This is Rn. And I have a set in this which I would like to define to be a manifold, or check the definition for it. This would be this M. And it is a manifold if for any point I can define a relatively open set within M, which is diffeomorphic to something else which lives in a completely different space, but which I also know well. So this will be Rk, sometimes called the modeling space. This is locally I model this structure after the structure of Rk, in which I have some open set U, which should be a smooth image of something in here. Okay, so there comes the, and for any x. So I should be able to do this for any x. Note before I go into this that this is a local construct. I'm not saying that globally my surface looks like something else. I'm just saying that locally, if I take small enough neighborhoods, then it looks like, up to smooth deformation, a set that I know well, an open set in RK. But I need to clear up one thing. What's an open set in a manifold? The only open nest comes now from the topology of Rn, in which I know what open sets are. I have a way to measure distance, and an open set is something that such that for each and every point, it has an open neighborhood that's still in the set. So I can draw a little ball, right, which is small enough that's still in the set. So we have that notion, and I certainly rely on that notion here, right? So an open set is that I pick any point in the set, then there will be a small enough ball that's still in the set. Okay, that's just the classic notion of openness, for which I just needed to have a good distance in that space, a notion, or that is not the case here, because the minute I start talking about subsets of this that I envision to be diffeomorphic, I'm not moving in the full space anymore. It's not going to be an open set in the full space. So how do I define an open set on a potentially really bad set, which can be a rock for all I know, right? With all non-smoothness and everything, but it certainly has a lower dimension in general than the space, right? So the way to go about that, and this is a standard construct in differential geometry, is that you basically transport the openness notion that you have for the full space to that little set that you want to work with. So the way to generate relatively open sets in the full space is that you actually take an open neighborhood of X in the full space. So take an open neighborhood, which would be, I call it W, and that's in Rn, and that's open in Rn. And it's an open neighborhood of that point X naught, what did I call it? X, okay? So that's the point X, an open neighborhood of X, and in Rn. And then you simply intersect M with that large open set in Rn. And whatever the intersection comes out to be, you call that relatively open. So this V, which you generate as the intersection of W with M, is what we call relatively open. So that's the way to generate these local sort of open set, open neighborhoods that are required in the definition. We know that now. Okay. Once again, what I've drawn here, this set, look at this. This is not open in the space, in the full space. Okay. Because at any point here, you draw a little ball which is open in the full space that's going to stick out from the manifold. So that's not an open set in the usual topology of Rn, but we call it relatively open within the topology of the manifold. We don't know yet what the manifold is, but I can do this for any set. It doesn't have to be a manifold. But back to the statement is that now I have to have a differentiable diffeomorphism mapping one of these sets into the other. So I have to be able to go both ways. I have to find a mapping that in fact takes me from here to there. And in this direction, I call it phi. And that phi is a mapping from U to V, right? And the other direction, I call it phi inverse, because that's what it means for diffeomorphism to exist, that it has to be invertible, it has to be smooth, and the inverse has to be smooth. So this takes from V to U. In this context, phi is called a local parametrization. And phi inverse is called a coordinate system. because when I go, did I do it? No, it's the other way around. Sorry. Phi goes this way. I knew that wasn't right. So only realized, my apologies, when I wanted to explain why, right? So phi is this way and phi inverse is that way, because when you go this way, then it agrees with our intuition, what we would normally say, I'm parametrizing this surface. Say if this was a two-dimensional surface living in R3, then this would be, if it's two-dimensional, K would be 2, so this would be just a plane with S1 and S2, right? And then we are familiar with that when we do multivariable calculus and integral involving surfaces. And then we would use this, you call this S1 and S2 the parameters that parameterize locally, right, this surface, and we would even imagine that, okay? So that's the usual terminology. And going in the other way, we say it's a coordinate system, because you say, okay, I start with the surface and I want to coordinatize with the surface. I want to introduce coordinates on that surface. So this is just terminology. Okay. The intuitive meaning, as I said, which I wanted to point out, which I think I will be using in examples, this intuitive meaning, that is that a k-dimensional manifold locally looks like an open set. And an open set in RK looks like RK if it's going to looks like RK. And that K, mind you, has to be, which is the dimension of the manifold if it comes out. So K is then the dimension of the manifold. As I said here, it has, I did not associate that with the point. I declared K first, and then I said that this must hold for at each and every point. So you cannot have a varying dimension for the manifold. That's no longer a manifold, right? So K-dimensional, it has to be the same K everywhere. That's very important. So something that's a two-dimensional surface cannot at some point turn into a curve and then into a three-dimensional space. That's not a manifold. K has to be the same for all these. Now, there's one thing to remark here, which is if you're a careful processor of what I'm doing, which I probably wouldn't be because I would just be taking this in, but most of this is clear from multivariable calculus except for one thing. Let's see that one thing is. So most of this we could already do just based on this definition and knowing multivariable calculus. I can certainly take a mapping that takes from RK, and its image happens to be just this set here, okay? It just so happens that it doesn't span the whole image space as it could in Rn. It's just every point that I take here just sort of collapses onto this one. And I even know then it's a function, phi is a function of the coordinates in RK. I even know how to differentiate that, okay? I also have no problem defining its inverse because all I need to do, phi inverse, because I just say, okay, so this point went to that point, then hey, then the inverse of that is this point going to that point, right? No question. However, the minute I say diffeomorphism, that I'm requiring more. I need to differentiate phi, but I also need to be able to differentiate the inverse. And how do I differentiate this mapping, which lives in a potentially bad subset of RK, right? Because we know how to differentiate mappings between Euclidean spaces, or at least whose domain is a Euclidean space, right? We learned that partial derivatives. But I don't have that here because it's on a funny non-open subset of the full space. So one thing is to know so the question is that how to make sense or compute this. Okay, because this is not, because phi inverse is not defined in an open set. Of Rn, right? You see that, right? So when I talk about this, how do I talk about this? So then I need to then clarify what's the derivative of a map, which is generally speaking just a mapping from something, any set, and that can really be a piece of rock, it doesn't have to be a manifold, okay, into Rn, and X is say, you know, a subset of Rm. It's a general set. So this is a mapping from a general set. It can be a completely bad set, right? Now, how do I define the derivative of that? So we'll say that we say, what was that? That's the, that is, we say that F is a smooth map on X. And mind you that X can be pretty bad, like I said, also whatever, cusps and discontinuities and all that, if it locally extends to a smooth map between open sets. Of Rm and Rn, okay? So maybe you did have that piece of rock here. So this is your X, right? And I'm not trying to say that this is a manifold in any sense, but I do assume that it does live in Rn, Rm, sorry, that was the, in this case, that space. Although if I want to be consistent, I'm going in this direction. So if you excuse me, I will change this too. Not that I'm not, what I'm saying is not wrong, but if you want to have the one-to-one correspondence with the notation that I had there, so this is a mapping now to Rm, and X is in Rn, at which point my inclination was correct to say that this is in Rm. This is Rm. Okay. And now we have this mapping that take this mapping F that takes you then to Rk, no, sorry. X is in Rn. No, X is in Rn. My apologies. X is in Rn. Okay. And that takes you to Rm. Okay. And I had this point here on this bad set. And in fact, let's put it right there in a really bad location, right? So little x is in X. So how could I say that this mapping, when can I say that this mapping is differentiable smooth? And the idea is the same idea that we had here. If you don't know what to do on a lower dimensional subset, then use the fact that you know what to do on the whole space itself. So if you can extend this map smoothly at any point to an open set, so that on that open set, it becomes a nice smooth mapping between that open set, then we can call that now W, which is in Rn and open, and this is now some target U, okay? Then we call it smooth, right? Again, the assumption is that at each point, X, F extends smoothly. Now, why is this helping me? Because the minute I have a mapping which extends smoothly to an open set, then I can deal with its extension, which is now a bona fide mapping between these two open sets, okay? And once I have an open set in the domain space, I can take the derivative of the mapping. I know how to do that. I can take partial derivatives in a Euclidean space in all directions. And once I'm done with that, okay, I simply restrict that to this bad set that I have back again. And I can then We'll see in a second how that actually works, but this explains how one can make sense of the smoothness of the inverse of phi of phi. Still need to check that in a given problem, but let's see that. So any questions on this as I write out? So I just want to do an example. What's the pendulum for dynamical systems as the example for everything? Then I could say that, you know, for manifolds, the example for everything probably is the circle, the simplest non-trivial one, right? So the circle S1, which I can picture as I'm doing right now as something that lives in R2, okay? So I'm faithful to the setting that I have set up. So this is in R2, but it's unclear if I want to say it's nice, but is this a manifold? And a quick non-informed understanding of the definition would say, well, I just have to check if this is diffeomorphic to some Euclidean space or some open set in some Euclidean space. That's unlikely that the circle is diffeomorphic to some open set in some Euclidean space. It doesn't look that way. And it's not, actually, but that would be a misinterpretation of the definition. The definition never says that the whole set M has to be diffeomorphic. It just says that it has to be locally diffeomorphic, which means that at each and every point, I have to find an open set, okay? Relatively open, which I get by taking a large open set and then intersecting the circle with that. And that's how I get this relatively open set, which is then in turn diffeomorphic with some open set in some space. And that looks fine, because I certainly can think of one such space that would be R1 or R, in which open sets do look like what I have here up to a deformation, because open sets here have a curvature, right? And the open sets in R1 are like this, they're straight. But that's just being handled by the diffeomorphism. Never said it's the identity mapping, right? So that's my hope. So if we want to show that S1 is a one-dimensional manifold, so that means that K equals 1 in the definition, then they need to establish local parametrizations that do have that property. Now, in principle, it's enough for me to do that for each and every point separately. That's enough, but it's also very tiring, right? So if I can get away with covering lots of points at the same time, why don't I do that? So here's, I just needed that, those two lines, because I want to divide the circle, one convenient way, into 4 parts. And I'm going to take care of the parametrizations for those 4 parts. So this is, say, X and Y. And I define 4 subsets. So one subset would be this large open set, which varies from here to there. And it doesn't contain the endpoints. I call this one V1. Then I will have another open set V2, which doesn't contain the endpoint. And I'm being ambitious here because the notation already suggests that I'll be using these as the relatively open subsets. In other words, I'm not going to be messing around with each and every little x, but I'm going to be covering all the x's, right? And that all x's will be good for this parametrization. So these are relatively open sets. Presumably we see that already because I can generate them. I take open sets in the space, right? They're like this, or, you know, so they're like that. And these V1 and V2 can be generated as intersections of those, right? With the circle. And then I will just say, look, if this part, this is already, I can establish a relationship between this and, you know what, between this open set, which is part of R1 already, just by simply projecting it down. It's a one-to-one smooth operation, right? So I will have a mapping, one type of mapping that takes care of part of the problem, phi1, which if I introduce the coordinate, let's just say t here. So what I'm doing here, I'm cutting corners, and the abstract second picture that I, in my mind, is a completely different space. I'm also already inserting it in this picture, right? So this will be the space R1 from which I'm picking the parametrization, okay? And phi1, the first mapping, which, mind you, has to come from the parameter space and has to go to the manifold, and therefore has to go from here, has to be a mapping to the manifold. It's just very simple. I will take t is the element of R1, and the image will be just t itself and square root 1 minus t squared. And this is the radius is equal to 1. So that U space, the U1, the domain that I'm using for this parametrization, is just minus 1, 1. And that clearly works. It's a relationship between the two. As long as I'm not at 1, this is a differentiable function. Then you see why I've excluded 1, right? Because the dfi, I'm going to have several of these. That's what I'm right. Oh, no, yeah, but they're not going to look the same. So the derivative of this mapping with respect to t is, strictly speaking, I need to take the transpose of that, right? Because that's how I get a column vector in the image space. So then the derivative of this with respect to its argument is 1, because I differentiate the first component with respect to t, I get 1. And the derivative in the second slot is minus t over square root 1 minus t squared. And this is a perfectly nice smooth mapping as long as t is not equal to 1. And you see that's why I didn't go up to 1 here and there. t1 and minus 1, this will no longer be differentiable. Okay, so that's why I excluded it. And that's why I was not ambitious to have a larger set. Okay, now I can do phi2. Why do I need phi2? Because I haven't covered the full. I had to stop here because my mapping, the nice one that has been taking care of the parameterization, was blowing up here. Okay, so I can do that same trick here, right? And then phi2 would be t minus square root 1 minus t squared transpose, because again, that's how we get a column vector in that space. And the U2, the domain of that would be U1. Remember what this U was. U was the open set in the modeling space. So I'm modeling now a part of the manifold here in the simplest case. And U1 lives in R1. So therefore, K equals 1 in my attempt to parameterize this system, this circle. I can calculate the derivative in a similar fashion. I'm not going to do that here. You see that it checks out to exist as long as you're away from those 2 points. Have I solved the problem? No, because of those 2 points, right? That's annoying. I have not shown that each and every point admits a local parameterization because those 2 headache points. So what I do now, I over-parameterize, if you will. So I would say, okay, just to cover the rest, in fact, I introduced these 2 other open sets. So one here and another one there. I can use as many as I want, as long as I, in the end, cover the whole manifold candidate. So this will be V3, and this will be V4. Okay, and then for those, the phi, the parameterization will be very similar, because phi3 will be just minus 1 minus t squared. So this part here, that's my t according to my notes, but is that correct? So so it returns negative values. So that's not right. For the first, no, it is right. It's the first coordinate. What confuses me is that I should really write this as a column vector. So all the first coordinates here for this piece will be negative, right? So it will be minus 1 minus t squared t. And then for the other one, phi4, and I should say this is a mapping in t, right? Phi3 t and phi4 of t equals plus 1 minus t squared t if all goes well, right? And then I could take the derivatives. The reason why I started talking, and you see that derivatives are okay as long as you're staying away from all those points. I also wanted to use this to illustrate what I was saying about the d phi inverse, how you get to that. Because I have checked, so phi and phi is smooth, phi is smooth, phi i's are smooth and invertible. But I would still need to check, because it's not given, that the inverse is differentiable, right? So the phi, the inverse, I need to look at the inverse and see when I can, if I can differentiate that, all right? So check the differentiability of inverse, or smoothness of the inverse. So for instance, for I equals 1, and the others are similar. So for I equals 1, this was the simplest mapping that I had. I had phi 1. It was the very first one I did here. So that's t as square root 1 minus t squared. Okay. And I had the derivative that's already in store for me. What's phi inverse? Let's write it out. So phi inverse, what it does, it takes a point on this V1 and simply projects it down. But it's really only defined here. So what it does, I have to say exactly what it does, it takes a coordinate t and 1 minus t squared, right? And maps it to t. That's what it does. So see, this is really restricted to the circle. So here's the problem that I was describing, that how do I take the derivative of this mapping, which is defined on a funny curved surface rather than on the nice Euclidean space that phi1 was defined. And see, I had no problem taking the partial derivatives in what I was doing here. You know, I only had to take one derivative with respect to t. That's what I did here. But how do I do the same here? The t doesn't live here. The t was living here. This is just a target space that is curved. So how do I do that? And the recipe was extend this to a smooth map, which is no longer just a map on the circle, but a smooth map on the whole space. So extend to R2, where this lives. So in R2 is, say, the x coordinate, and that's the y coordinate. How do the question is, can I extend this smoothly? Can I extend this to a map that does exactly what this does on the circle? So when I restrict it, it's smooth, but when I restrict it to the circle, it does the projection. Sure, it's just a standard projection on R2. So the extended map, F tilde, would be just taking, you know, any point on x, y, and projects it down to x, because that's what this mapping does. But this is no longer restricted to the circle. This projection map now operates anywhere, right? And when I happen to restrict it to x, then or to S1, then it just gives me the projection. So this map I can certainly differentiate. So this is the target, just x one dimensional. And I need to, sorry. Did I write this in the right direction? So what I need to do, I need to take the image, and which is x, but where does it map? So it maps back to the one-dimensional space, right? So I need to take the image and differentiate it with respect to X and then differentiate it with respect to Y. Okay, so when I do this, first I differentiate X with respect to X, that's 1, and I differentiate with respect to Y is 0 because it doesn't depend on that. Okay, so this I could execute without any problem. And again, the way I got this is first I differentiated, you know, the image with respect to X, and I differentiated with respect to Y because these were the two arguments that went into the mapping. And this is how I got that. So this is certainly executable and nice and smooth, and I can then go ahead and restrict it to the circle if I want to for further calculations. So this is also okay. So that's the way then, just in a particular example, to extend X to what confused me for this, that in my notes that I went with row vectors and column vectors, and I just needed to resolve that. Okay, so that would establish all together is that S1 is a one-dimensional manifold. But it's not globally diffeomorphic. To R1, but that's never required. It's never said to anybody that it has to be the case, okay? Let's look at an example of things that are not manifolds. And now I will use the intuition that we have partly and partly sketch the arguments why these are not manifolds. So examples or sets that are not manifolds. A favorite example in almost all books is the figure 8, which you can also think of as the double homoclinic loop of the Duffing oscillator. So when I said a stable and unstable manifold, and now I'm saying this is not a manifold, was I inconsistent with the terminology? Well, somewhat, right? Because let's see if that was the case. If I talk about this, so this is the figure 8, and I claim it's not a manifold. So yet I was talking about stable and unstable manifolds when I was talking about the Duffing equation. So if there's this point, and this is the equilibrium point, okay, then the unstable manifold is what? The unstable manifold starts from here and goes there. And does it go through that point? No, because the definition of the unstable manifold would be that it has to convert, well, you know, it has to get closer and closer. We didn't consider this point again part of the unstable manifold. Okay, we consider the unstable manifold as a set of points that ended here, and the same here. What's the deal with the stable manifold? So the stable manifold is the set of points that are definitely not the object itself, and they have a non-zero initial distance, and they will converge to that. So again, point. So we left that one out. So when I was claiming that this structure, for instance, the one that I'm showing you right now, I still maintain that that's a manifold. But I will say that once I connect it through that point and I get the figure 8, that's no longer a manifold. So why is that the case? You could ask, because this locally doesn't need to look like an open set in R1 or R2. We kind of have an intuition that locally here it looks like R1. So it looks like R1 locally. And if I check it here, this is a relatively open set, just in case, just like in the circle case, this looks like R1. So apparently, locally, when I do the check, it does check out to be a one-dimensional manifold at each and every of these points. So the problem point must somehow, we all feel, be this, right? So why is that problematic? The reason why it's problematic is that if I now go ahead and take an open set of this point within the figure 8, and I execute my procedure for creating a relatively open set, so this will be my ambient W, okay? Then no matter how small I pick that W, any relatively open set, I will magnify what that is here. Any relatively open set will have this X shape. And then it ends here. It always looks like, and it doesn't matter how I pick how small W is, as long as it contains this point there, what you have here now will be a relatively open set. So a relatively open neighborhood of X. That's the point X there. X in the figure 8. And the intuition says, before you do any mathematics, that's why it's helpful to have the intuition that, wait a second, it doesn't look like anything that would be an open set in R1. You could say, yeah, but why do you insist on R1? Maybe it looks like something like an open set in some other space. But I say I'm stuck with R1 because I started checking whether I have a manifold or not. And at these points, it's locally a manifold and gives me R1. I cannot divert from that because I have to have the same dimension no matter where I check. So I'm stuck with R1 as a candidate. Okay. So is this an open set in R1? And the first answer would be no. It's not like that. So I would like to conclude immediately that I won't find any diffeomorphism that maps this X with the open legs into an open set in R1. Now, when you actually have to show that, that's a little bit hairy, actually, because it's harder to show that something is not a manifold than something is a manifold. Because if you show something is a manifold, you just have to come up with one parameterization that checks out. To show that something is not a manifold, you have to show that such a parameterization doesn't exist. No choice is possible, right? So it's a bit harder. So one way to show that, I will just sketch that in words, but this would be that it does not look like an open set, right? That's why I said the intuition helps. And to be honest with you, and now as I think back to it, when I took differential geometry in graduate school, this is what the instructor said, and that was a math class. So clearly it's not a manifold because this doesn't look like an open set in R1. And then we went on. And I still remember wondering, yeah, but the look like, that's a fairly relative notion, right? I mean, how could I actually prove that this is not diffeomorphic to an open set in R1? And I'm not going to do that in detail, but just give you maybe a sketch that if this is diffeomorphic to an open set in R1, then let's just take this open subset of it, right? So it has to find its place somewhere here under a diffeomorphism under that open subset, okay? And let's take this other subset here, okay? And it has to find its place somewhere here, but because it's a nice smooth mapping, then precisely I've excluded that one single point, okay? By continuity and differentiability, the way these two are related to each other is that they are really, actually I show them here. So I take this part here. So somewhere it will be there. I don't know exactly where. And then I take this other part here. It will have its image somewhere there. Because under a smooth mapping, a connected open set must map into a connected open set, no question. And in fact, by continuity, if I left out this single point, I'm running out of colors here, but maybe that's the one point that has to be mapped there. Okay. Now, what about these other ones? Well, this other one, and this is, I'm not going to use the colors now, but this is another open set, right? There's certainly room here. It could be mapped someplace in there, and there's room here. It could be someplace in there. But whatever that is mapped, its closure of that set must contain this point. And see, there's no room for that here, because if that open set is mapped here, even if I close it, it will not intersect that point. So somehow that open set would had to be contained already in the image of this, right? But that wouldn't work because this is supposed to be a diffeomorphism. So it would have to be one-to-one. So I can't map the two different open sets onto the same point here. So you can work this out. So again, this is the point, but you get a contradiction. Just this is usually the way to establish a contradiction, that, okay, I can accommodate, you know, this open set, but then that open set, but hey, this is a smooth map. So when I take a limit of points here, that they must limit on the same point there, and they must limit on the same point there, and from here. And the topology of R1 doesn't allow that, right? You can only approximate, come to this point from two directions. So you would have to contain one of the sets would have to contain the other, but it doesn't work for diffeomorphism. Okay, so a long-winded explanation. The short story is that doesn't look like an open set in R1, right? At the end of the day, what are the other? Are there any other examples? I had another example, which is this is sort of A, is the figure A. B would be actually let's look at a quasi-periodic orbit on a torus. So we've already talked about that in terms of the Hamiltonian systems. Quasi-periodic dense orbit in T2. We know how to generate these, right? If phi1 is a coordinate on the torus, then this differential equation phi2 equals omega 1, phi1 equals omega 1, phi dot 1 equals omega 1, phi2 dot equals omega 2 in the case when omega 2 is not equal to p over q. P over q are integers. Okay, q is non-zero. So these are relative what's the word, incommensurate frequencies, right? So I can't write them as relative primes. Not relative primes. I can't write them as a quotient of two integers, okay, that are relative primes to each other. So we've seen what that gives you is that the topology of the orbit will be, there's nothing non-smooth about the orbit, but the orbit itself will be winding around in the torus like that. And it will be dense. And you would think that, and I would think that when it does that, it's the nicest structure you can think of, right? What is it? It's just a trajectory and it's smooth. And one can also then immediately make the association, wait, this is just a trajectory. So there's a mapping between R1, the time, okay, and this trajectory, in fact, globally. So it seems like this is a manifold under our current construct, because I immediately have this mapping between the whole of R1, which is a subset of R1, certainly, and this winding. So is that the case? Well, we need to still check the definition. So what is the manifold candidate here? It's not the torus. The torus turns out to be a nice manifold, but this is M, the trajectory. So what do this whole picture is in R3, because I needed a two-dimensional torus to make this picture happen, to embed it nicely. And now I'm checking the definition, which would require me to do little open sets in R3. So this is W, an open set in R3 that then intersects the torus. And I will then blow up again in the intersection, and I have to be ready to make W very small around this point X. So this is X. So this is my point X. So this is now a relatively open set on what? On the torus? No, my manifold candidate is M. So I need to figure out the intersections of M with this W. So a relatively open set in M will be what I'm showing here. These infinitely many open intervals, in fact, densely accumulating on each other. So V is the relative open set in M. Okay, it will be a dense set of accumulating intervals. when I say intervals, they are curved, right? Because they live on the surface of the torus. But individually, they're very close to the sets that we were using on the circle, right? A small deformation, individually, it was straightened out, no problem, okay? And you know what? If I had finitely many of these, then I wouldn't even have a problem. X, by the way, has to be in one of them, right? Because if I had finitely many of these, so the orbit was not quasi-periodic, then keeping W small enough, I could achieve that ultimately I'm only intersecting one. And this I've already seen is diffeomorphic to an open set in R1. But my problem here is that I cannot achieve that in the case of a dense orbit. It doesn't matter how small a neighborhood I pick, there will always be infinitely many. And again, now I just rely on your intuition, but you can complete this again, playing with the implications of what this dense set of sets would imply, that this is not like a single open set in R1. Okay, so much as we would love that. Interestingly, however, if I change that quasi-periodic orbit to periodic, it doesn't matter how many rounds it does. Then if I pick then V small enough, then I will able to always pick relatively open sets that are really like intervals, and then I'm done. But for a quasi-periodic orbit, I can't do it. So that's not a manifold, interestingly. And the reason is the density in this direction. Because again, you will be able to select a set of points that will have then convergence requirements from the other direction. I could individually place these, in there, okay? But then they would have to be able to approximate each other in the image space as well, because the mapping is supposedly a diffeomorphism that takes me from there, and they all are separated from each other. So there's no way that I can reproduce the individual points of them could have points of accumulations into each other, because for this transfer series, that's kind of or sequence, that's the idea. And
sorry,
yeah.
Could you just repeat why, in the case of the periodic orbits, it's a manifold?
So in the case of the periodic orbit, maybe I was too quick with that. This picture, so first of all, I cannot draw infinitely many, right? Of these, just finitely many. Mm-hmm. But these are dense. Now, if I had a periodic orbit, which means that I would really just have a finite winding, potentially fairly tight, but finite, right? Then I can keep this neighborhood small enough, even smaller, that at some point I will only get one intersection. Okay. And when I have one intersection, then I would say, all right, for that particular small, relatively open set, this is what my set locally looks like, a nice open curved interval. I can certainly map that to R1, right? The problem in the current setting that this picture is self-similar. It doesn't matter how small I pick W, I keep getting infinitely many, right? Whereas in the case when you have a finite winding, when you make W smaller, you get fewer and fewer and fewer and fewer, and finally you're down to one. And that one single curve in piece arc is diffeomorphic to an open set, R1.
It's due to the finite property of the periodic orbits.
It's the finite property. So when these are rationally related to each other, then after a while you will close up because they will have a common period.
Thank you.
Yeah, you're welcome. Okay, anything else? So the last one would be, again, is things we've already seen and probably thought that they are the nicest manifolds based on what we already have. So it would be a semi-infinite spiral. So a semi-infinite spiral, by that I just mean the nicest trajectory that you would see at a focus, at a stable focus, right? And of course it goes on and ever and wraps up tightly and it's just that the automated features of my drawing routine take over sometimes, and they have a different idea as to how the picture should be finished. So this is, I mean, the endpoint as well. So you can think of it, trajectory of a stable focus. But not just the trajectory itself, plus the equilibrium, plus the fixed point itself. It's a nice continuous entity, right? So what would be the candidate set here? Let me pull this down a little bit. For if I say this is a manifold, what would be my candidate dimension? Well, we would agree that it's 1, right? Because if I try my luck and I look, you know, I might take my usual, this thing lives in R2. I take my usual external open set, which is the W living in R2, then here locally, I seem to have some luck because certainly it gives me this little open set, and that does look like R1. So it works there, it works there. So therefore I have no choice. This should, if it's a manifold, it has to be a one-dimensional manifold, right? So at any point it has to look locally like R1. So where's the problem? The problem in these examples is always with the accumulation here. Because if the endpoint is included, which I have included, why don't I just set up, you know, my W around here? So that's centered at fixed point. The center is not so important. What's important is that now I'm trying to verify the manifold nature at all points, and therefore, since the fixed point is part of the manifold, I need to be able to verify that for X being the fixed point. And to that end, I need to set up a relatively open set in this manifold. So what's a relatively open set in this manifold? Let me blow it up again. A relatively open set in a relatively open neighborhood of X, which is, let's call it X. So that's somewhere here. That's just X. And a relatively open neighborhood of X would be a piece of the trajectory that comes in, so it's part of it is open, and then it just spirals in endlessly. So again, we have the same self-similarity, okay? So certainly this doesn't look like, again, at this level of hand waving, doesn't look like an open set in R1, right? So these all worked, all these other sets here and there and there. In fact, for every point, I can set it up this way, but not for that one. That also shows, because for every point I can set it up this way, that if I remove the fixed point, so when the fixed point is removed, it's actually a manifold. And then you could say, wait a second, I mean, just because I remove the fixed point, it doesn't change the picture at all. Because, all right, that it's now punctuated, that certainly any set like this, no matter that it is centered around that point, no matter how small it is, will contain an infinite piece, which with its own self-accumulations and everything. So what's the answer to that? The answer to that is that that's obviously the case. However, I don't have to do justice to that point anymore. Okay, I don't have to center a neighborhood around that point anymore because it's not part of the manifold. So I'm not claiming that at that point the manifold definition has to check out. So what that means is that now I can punctuate that. All right, and I still have an infinite spiral, but I only have to do justice to points that are at some finite distance from the endpoint. And the minute you pick something that's at finite distance from the endpoint, okay, which is here, okay, then for that, you will be able to pick a small enough W. Then your relatively open set U will look like this. In the particular case that I have picked here, right? So I don't have to worry about this point in the middle anymore. In fact, I can't because it's not part of the statement. But the minute then I pick any other point that has a finite distance, all right, and that infinite winding in any finite distance becomes a finite winding once I'm in a finite distance from the endpoint. So this is then, it turns out to be a manifold. Any questions on that one? While you're thinking, the next example, I have no next example because I have to give you back the 5 minutes. All right. So I'm stopping now, and the next lecture will still be, I'm not going to talk as much as I did today because I wanted to make sure we understand the basics, the fundamentals of what a manifold is. And then once we understand that, I can build the little bit of machinery that I need, basically calculus on manifolds, a little bit of that, tangent space, tangent bundle and all that. And then I can move on to the actual theory of normally hyperbolic invariant manifolds. But these basics were important and not necessarily intuitive if you only know Euclidean geometry and Euclidean calculus, multivariable calculus. Okay. Any questions? One bit that you might need for the homework is that which I didn't mention, but that's part of the homework, is that the graph of a smooth function is always a manifold. That's a statement. So I just list that now. So no. The graph of a smooth function is always a manifold. And that just means graph in the most general sense that you have some domain space and you have some image space x, y, and the graph, and you have a mapping from x to y. The graph of the mapping F is defined as the set of ordered pairs x, y, such that x is taken from x. And once you have taken x as a member of x, then the corresponding y is just equal to f of x. Right? And that's a usual notion of that. We draw it like that. So that's graph, the graph of F, but don't think of it as an image anymore or a illustration of the function, but think of it as a geometric object. So this will be your candidate for a manifold. And all the homework problem is to show that this is a manifold, but not just by drawing, as I have done. This is now an arbitrary high dimensional space, and the graph can be, pretty active and moving around. And F is smooth, but I didn't say F is a diffeomorphism. I just said it's smooth. So potentially it may not be even invertible. And certainly the inverse, even if it exists, doesn't have to be differentiable. So I just assume that it's smooth. And then show that this object that I have just defined here is always a manifold. How do you show? Well, the way to show something is a manifold, you have to construct local parametrizations with the appropriate k-dimensional space and show that those are then locally diffeomorphisms. Okay. Any question? Okay. Anyone?
Yeah, I have a question.
Yeah.
This quasi-periodic trajectory on the torus.
Yeah. Mm-hmm.
If you would embed it in a higher dimension, could it become a manifold?
The periodic is always one, right? You said quasi-periodic.
Quasi-periodic, yeah.
Uh-huh. I think that the problem is that even if you embed it in a higher dimension, on the torus, right, it will always be dense. Okay. And whenever you take an open neighborhood of any point of that in that higher dimension, it will unfortunately always contain an open neighborhood of the torus. And within that open neighborhood, the trajectory will be dense, and that's what's killing the construction. So even this could be in principle, for all I know, a 4-dimensional space, right? And the trajectory in that torus is still dense, okay? And the torus contains the trajectory. So when I take a relatively open set in this dimension, so this is now, R3, but this is R4, then whenever I take the relatively open set, so that will be then a 4-dimensional set, okay? But it will still intersect the torus as well, because the torus contains the trajectory. And within the torus, the trajectory is dense. That hasn't changed, okay? So the intersection with the torus of that high-dimensional relatively open W will still be this, because the torus itself is 2-dimensional. So irrespective of the ambient space, that intersection, when I view it on the torus, will look like this with all the pathological issues that I had.
Okay, thank you.
I find this kind of surprising, this example, just by removing the endpoint, because the accumulation is still there, right? In the case of the torus, we could only fix the issue by passing to a periodic trajectory, so basically removing the accumulation, right? But here, the accumulation with the focus is not removed, but we remove the endpoint, but that already fixes the problem for the reasons that we have just discussed. That then at that point, then each point will have a finite distance from that point of accumulation, and if you pick a small enough W, again, then ultimately you will be looking at locally a set like this, which you can easily parameterize from R1 using an open set. Okay. There are, however, notions that some of you might take then differential geometry later, and you might learn that the quasi-periodic trajectory is after all a manifold, and then you will be cursing me out that I taught you wrong. There are different notions of a manifold, and there are relaxed notions that don't require that. And there's the notion of an injectively immersed submanifold that would actually allow for this. But the classic definition of a differentiable manifold doesn't allow for that. Because remember the homoclinic tangle, that the manifold starts self-accumulating, and I still call it a manifold. But in fact, that self-accumulation that happens there would invalidate the definition of will invalidate the classic definition of a manifold for the unstable manifold once it starts tangling. So you could actually make a point that there's a clash in terminology, and there is indeed one, but there's a weaker notion of a manifold, which we will not be using in this chapter. We need the stronger notion. That would be actually calling this a manifold. That's called a injectively immersed, which doesn't require that there has to be a diffeomorphism. That there just has to be a nice map, and it has to be 1-to-1. It has to be okay in one direction, but not in the other direction. Okay. Anybody else? If not, sounds like we're done for today. So enjoy the rest of the day. See you next week.